All right, good afternoon. Welcome back to Calculus 2. Here we have the definite integral. It's a change from 1 to e dy over y square root 1 plus natural log of y squared. So the first thing we're going to have to do, because I only know a couple of integrals that have natural logs in them, a lot of them have to deal with integration by parts, and putting integration by parts on top of this seems like kind of a scary thing. It could happen, but I don't think I need any for this problem, for this test. So what we're going to do is we're going to go ahead and set u equal to natural log of y. While I'm doing that, I'm going to say, you know what? When y equals 1, u is equal to the natural log of 1, which is 0. Oh, that's convenient. When y equals e, u is equal to the natural log of e, which is 1. Okay, I'm feeling pretty happy about that. Okay. We took our u is equal to natural log of y. Du is equal to 1 over y. So let me go ahead and break apart this integral a little bit so we can see what's going on with this thing. So I have 1 to e. I've got a dy here. Let me just go ahead and write this down here. So I've got a 1 over y part, and I've got a 1 over the square root of 1 plus ln of y squared. Okay, so the first thing I'm going to do is go ahead and make some substitutions. I'm going to kind of dot a line around this 1 over y dy, that's du. So we go ahead and figure that out. So we're going to say this is going to go from 0 to 1 because we're in the u world now. And here we have 1 over y dy, that's a du. And I'm just going to write this as 1 over the square root of 1 plus u squared here. All right, and that's what we've got so far. This is in the numerator area, so it's on the main line, and then we have 1 over this piece here. Well, we have a square root of a square. That is telling me that, okay, even though we started off with like natural logs of y's, eventually we meander our way for like, this is a triangle. So we're going to do a triangle here. And because we have a plus here, right, we can go back to a squared plus b squared is equal to c squared. I'm going to make the two sides of my triangles a 1 and a u so that my hypotenuse is going to look like a 1 plus something. Okay, so we'll go ahead and make this a u, make this a 1, and we have the square root of u squared plus 1. And here's my theta. Right? So this only works for first quadrant stuff. 0 to 1 is first quadrant stuff, so we're not going to have a problem with this. Okay, we're going to say that the tangent of theta is equal to u over 1, or u is equal to tangent of theta. Du, and I got to go ahead and take the derivative of tangent, that's going to be secant squared theta d theta. And so I've got a plan for my du. Okay, so let's go ahead and break apart this integral so I can comfortably substitute. Do we want to change our limits of integration again? We could. So we could say when u is equal to 0, okay, we have tangent of theta equals 0. Inverse tangent of 0 is theta is equal to 0. When u is equal to 1, we have tangent of theta is equal to 1. Take the inverse tangents of both sides. We have theta is equal to inverse tangent of 1 is pi over 4. Remember, we have to work in radians and calculus, right? So we can go from 0 to pi over 4, and that will spare us the trouble of going and doing back substitutions. You can go back and do back substitutions, and that's fine, whatever floats your boat, all right? So we're going to integrate between 0 and pi over 4 because we are now in the theta world. And then what I'm going to do is I'm going to say we have a 1 over the square root of 1 plus u squared times du. Now, what is 1 over 1 plus u squared? Well, I'm looking at this, and this is adjacent over hypotenuse. I think that has a meaning in trigonometry. That looks like cosine to me. We have 0 to pi over 4. Here we have is a cosine of theta times, and then my du is theta squared, okay? Or cosine secant squared, rather. So this is going to be 1 over cosine squared theta, d theta. So we're going to go ahead and cancel out some trigonometric functions here. So we have 0 to pi over 4. And here I have 1 over cosine, which has a name, that's secant. And that's one of your integration facts, right? Being able to integrate secant is one of those things that we're supposed to know. So we're going to say, okay, we have secant of theta d theta, and this is our integral. So this isn't too bad. This is equal to the natural log of secant absolute value, secant theta plus tangent of theta. And what are we doing? We're going from 0 to pi over 4. Okay, that's not too bad. All right. We don't have a plus c because we have a definite integral, but that's what this integral boils down to. I'm like, well, that took that kind of a scary looking integral with natural logs in it and all that fun stuff to it's just natural log of secant theta plus tangent theta. That's not too bad at all. So going back to my unit circle, we have the natural log of the secant. We don't even need absolute values. These are all positive. So this is the secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0, just put a 0 there, plus tangent of 0. And we're just going to figure all of this stuff out. Well, going back to my unit circle, cosine of pi over 4, that was 1 over root 2, or root 2 over 2. And that's going to be the square root of 2. And so I have the natural log of the square root of 2 plus 1. That's my tangent of pi over 4. You're allowed to use a calculator. You don't have to remember your unit circle. That's okay. Minus, and then I have the natural log of secant of 0. That's 1, but tangent of 0 is 0. So the natural log of 1, again, you're allowed to use a calculator. Natural log of 1 is, you guessed it, 0. So my answer here is the natural log of the square root of 2 plus 1, and that's what I'm going to go ahead and box up for my answer. Now, I want to show you one more thing. If you have a definite integral, you can type this into Desmos, and I highly recommend that you do. And I just typed in int for my integral, and it puts your cursor automatically where you're supposed to go. And I typed in a 1 to e. That was my original problem. If it's an indefinite integral, you can pick like 100 or 1,000 for infinity, or negative 100, negative 1,000. So you can kind of get an estimate of where you're supposed to be. And then I just typed the integral in as x's because Desmos likes x's, so it doesn't like y so much. It'll work with y's, but it tends to like x's. So I just typed the variable in, I just typed the integral in as it was, and then we got an answer, and I'm looking at my answer all the way out to like the 10 decimal places, which doesn't exactly say it's going to be the same. But when I type in my natural log of square root of 2 plus 1, which was my answer, these are looking like the same thing. This was my final answer for the problem that I solved. And this was the original, the problem that was posed in the problem. I got the same thing. I'm pretty confident that I'm feeling like I got the right answer out of all of this. Okay, so with definite integrals, you could definitely plug those into Desmos and see if you're getting the same answer. If it's not going to, if you need something other than that, you could do like an integral from 1 to 2 and then plug in yours to make sure you're getting the same numerics. But you can, there's multiple tools for you to check your work to make sure you're getting the correct integrals, and you can kind of check with, hey, am I doing this right? Or am I getting the right answer? So you don't technically need an answer manual or a back of the book in order to make sure that this works. Okay, so I just wanted to show you that. I'm going to say thank you very much for watching the video. I'll see you in the next one, and take care until then.